Okay, good morning everybody. I hope all of you are well. So let's start today's course. Do you have any question about previous week's course before starting? Is everything clear? All right, today we are going to talk about the linear regression a little bit more in detail, and we will talk about assessing the accuracy of the models. That is very important. Today's course is kind of important in terms of understanding different models, and when you're studying different papers, different research in the future, today's course are going to help you a lot because you will understand how to understand the metrics and how to understand the differences of the models, how we evaluate the accuracy of the models, how we can compare them together. So we will see the most important metrics today for models. But at the beginning, we will talk about linear regression. We will talk about the understanding of how we can, if you have a couple of data, if you have a data set, how we can create prediction based on linear and simple assumptions to understand whole scenario, so that later when we are moving toward more complex models, we understand them well. So today, as I mentioned, we are going to start with linear regression. Then we talk about the standard error evaluation. We will see the equation. We will see how we can do the evaluation. We talk about the confidence intervals. We define it, what does it mean, confidence interval, and how we can use it to evaluate and discuss about the model that we have. We will talk about the hypothesis tests, and we will see how we can assume some hypothesis on the model that we have, and how we can accept or reject the hypothesis in order to prove our model, for example, accuracy or the relationship between data that I will talk about that. Relationship is an important term because whatever we have data, if it's like any data in any example from image processing or from simple data set, we need to find, the whole objective is find relationship between data in order to predict something. For example, weather condition is changing based on the time and changing based on some parameters that we can read. And we can do based on those some predictions. So because of that, we should talk about the relationship between data. And finally, we will see some metrics for models' overall accuracy. So that one of them we already have seen, very simple one, but we try to also introduce a couple of more. So the whole objective is like to understanding all these in this lecture today. So let's start with the answering the simplest question that we can have. What is the linear regression? We can say we have a statistical method that models relationship between two variables, x and y, in simplest form. X was the vector of the inputs or features, and y was the output. We want to find out what is the relationship between input and output, so that if, for example, in simplest form, the value of input x is increasing, then the output is also increasing. Parameter that we are getting as input, whatever it is increasing, for example, in spam detection, number of characters of like money, dollar sign, and some specific characters that determines we have spam. If those are increasing, the chance to have spam email is increasing, for example. So whatever it is, we want to find the relationship between x and y. So for now, for simplicity, we will assume that we have linear relationship to understand the linear regression. The complex models, we usually don't have linear relationship between variables, but for now, to understand all the calculations, all the metrics, well, we will talk about linear regression and linear relationship. In future, we will extend it to nonlinear one, and we try to add complex and learn complex models. That finally goes toward, like, for example, deep learning models and much more advanced models that we will discuss them. So what we want to do, we want to find the best fit line. So best fit line is trying to describe the relationship between data that we have. So it can be used to make prediction of the y. So we give the x input and we want to predict the y, that what is the value per x that we are giving. So we try to, at the beginning, formulate this, and we discuss it today. So linear regression often considers as simple statistic technique, but it is significant, conceptually important for the practical implementations and whatever we are doing. Why? Because the most complex algorithms that we will learn in future, or you know already some of them, all of them, the understanding come from here. And if you want to not use them as black box, just import libraries or take some code, run, adjust the hyperparameters, and get the output. If you don't want to stand in this level, you should come from inside to see what is happening in background in order to be able to develop even those complex black boxes or algorithms later. So we want to say, okay, for relationship between data, we can have different questions that we need to answer. Let's have a look at the questions first, that what we want to answer. We want to say, okay, for example, let's consider advertising and the sales. So if you remember last week, we discussed about the advertising and the sale. You have some media, you want to spend some money to advertise, and you want to increase your sale. And we want to say, okay, let's have a prediction. How much advertisement on TV, social media, radio, newspaper can affect our, can change my or increase my amount of sales that I can have. So first question that we can state based on this problem is, does a correlation exist between advertising budget and sales? So of course, if there is no correlation, you don't need to spend money, right? But we want to see if there is correlation, we want to find it and understand it. Second question is, how strong the correlation between advertising budget and sale is? Is it worse, or the change is very slight? So you have, for example, to understand it better, you have a market, you have a store. Then if you do renewing the old building and everything, does it change the sale? And if it changed, how much? You can have hundreds of examples of different stores. They did renovation, and you estimate the money that they spend, and you see the sale after and before that process. Then you can say, if I do that here, make my store modern, better, more beauty, fancy, how much my sale is going to increase? Do I getting back that money in 1 year or 10 years? Hundreds of different questions in real life problems you can answer with understanding these relationships, with having samples, examples, and study them even with simplest algorithms like linear regression. That of course we will extend it to more complex algorithms later. So in simplest form, we can say, if variable increases in one, is it increasing the next one or decreasing the next one, depending the problem that we have. Other question that we can state is, which media channel have an impact on sale? And we can determine, okay, if there are different parameters, different x's, like TV, social media, newspaper, which one has more effect on the sale? And next question that can be how precise our sale prediction can be. So you have those data. We will see how we can make predictions. Then, but that prediction should be evaluated. That is also a large part of today's course. That we need to say, okay, how accurately I'm evaluating that. Another question that we can state is the relationship between advertising and the sale data linear, or it is nonlinear? We will also discuss it. And another question, advertising media channel works better together or better individually? This is the topic that we discuss it in next lecture, but that's also is important, as I mentioned that. So if we only advertise on TV, or if we advertise in both social media and TV, what's the relationship between this single and these two? We need to be able to evaluate and discuss about these two. So if you are familiar with, for example, deep learning models, is still how complex algorithm you know there, you must be able to answer these questions. So when we study advanced algorithms, but still we need to know how to evaluate, how to discuss, how to interpret our models and the results. So let's start with a simple example and we discuss it. So last week we discussed about the TV, radio, and newspaper advertisement. Here I plotted another example for you that you can see. We have some data that shows the newspaper advertisement. These are samples, and this is the X input, and this is the output, Y. So we have the sale here, and input is the amount of money that you spend. So these can be different markets and different samples that we have. This guy over here for this, for example, product, spent this amount of money, and the output of sale was this. And a couple of samples, and we have a linear regression model that gives us prediction. Again, very important to understand how we can read this line. This line means that if I look at this data as input, like if I give $40,000, for example, in this sample, as input, we draw a line here, and our prediction will be somewhere around 12 to 15. So this line helps me to predict the output. And we wrote a function for that. Sale is equal to f of the newspaper, radio, and TV. So first one newspaper, second one radio, and third one TV over here. And you see that the slope is more sharper for the TV and shows that it has more effect on the advertisement. And by simple looking, you can see that it is more meaningful. Now, let's define what is the dependent variable and what is the independent variable. Two terms that we are using a lot in machine learning techniques. You should keep this in your mind because we are going to use this a lot in the rest. So we say we call dependent variables as variables that we want to predict, so that or we want to explain them with using the independent variables. So let's define also the independent variable. We say independent variables are the ones that we believe may have effect on the dependent variable. Now with these two lines of definition, you tell me which one is X, which one is Y. Independent is Y. What about rest? No, what about the other people? What do you see? So variable that we want to predict. What we want to predict? Y. Then dependent is Y. Independent should be our inputs as X is so that we can say the amount of money that we spend on advertising is independent, so that the variable that we have over here. Now, on the other hand, sale revenue is dependent variable, so that dependent variable is the sale as output. So did we do mistake, or we talked correctly? Yeah. Okay, so is it clear? So is it clear? Any question? So based on this definition over here, we usually call the terms of the slope and intercept as coefficients or parameters that we have. So whenever you are reading as coefficient or you are listening as coefficient, we mean that we have some parameters that including the slope and intercept that we want to find them in order to predict our model. So slope is like how this line should be, and intercept how up down this should be. So that we want to find good values, some numbers, some numerical values put here that with calculating all this term, we have the output simply. Clear? We want to replace this with some numbers. What should be the number here that if this x comes, that y is the what I want. That's the whole idea. If I jump quickly, you may remember that if you are familiar with, for example, neural network, we are doing the same thing over there. Deep learning, we are doing the same thing over there, finding some parameters, but much more number of them that later we will discuss. But here, for simplicity, now we want to find the slope and intercept. How we can write this term? We usually write this term in this form. The y hat, the predicted y, whenever you see this hat, you read it as prediction of the model. So y hat, predicted y is equal to theta 0 hat, the predicted value for this parameter over here, added by theta hat 1, predicted theta hat 1 times x. And we usually don't need to show error over there because we said that this is not decreasable. We cannot do anything with this. It's not reducible. Because of that, we don't show that because it's not it's the reading error, the data set error itself. So now we can go one step more in depth, that we can write a prediction for y based on the ice value. It means that not only I want to predict all of them, per each independent, the ice prediction, I want to use the theta 0, theta 1 parameters as coefficients to use the input xi, one individual xi, to predict it. So it should be very simple and clear equation for you. Now, first thing that we want to define is what is the residual. The differences between the actual observed value of dependent variable and the prediction value of that variable can be called as residual. So the differences between those. That how we can write it? We can write it residual as E of the I equal to yi minus y hat of I. So where is the yi coming from? Somebody answer? yi is where? Where is it coming from?
Actual observed value.
Yeah, actual observed value that we have it in data set. So we are talking about supervised learning. We have the label of data. We have the output, real output. So this yi comes from there. And what is the y hat I? Output of the linear prediction or the prediction model that we have. We already give the input over there and whatever is coming as some output for i's value, and we compare that, the prediction, with real label that we have. For this real label, we have some x, right? We give it to model, and it gives us back the prediction. And we say, what is the differences between that prediction that my model does, and what is the real label? And I can compare the error over there. So that this is called residual. Clear? So of course we can have prediction for the x's that we don't have even label. But how we can do that? It's not that easy. But when we have supervised, that goes to our unsupervised learning. But in supervised learning, we already have label and get the differences. Then we have the residual. Now, if we know the residual and what does it mean, we can define the RSS and residual sum of the square definition that that as its name is indicating, it's sum of square of the residuals that we calculated, that it shows the differences between actual observed value and the predicted value of the variable for the model, so that we can write it in this form. How this equation is working, we can write RSS is equal to y minus the model that I have. So the label that I have and the model that I have and square of that. So for the parameter 1, for the parameter 2, for all the parameters. But my model, don't mistake this, these indexes should not increase because I have one model, the same model and the same parameters over there. Theta 1, theta 0, and theta 1. That we call it as intercept and slope. So what we usually write in machine learning, we write this term over here as y hat, predicted output. That this predicted output comes from the model that I have. This model in future will be very complex, very big, but still I have y hat as predicted output. Can I write it in summarized form? Yeah. The residual sum of square can be written as the sum of the differences between y and y hat squared. So that this gives me the RSS metric that shows how I can do that. So we will see in continuation why we defining this and why we want to use it. So everybody understood so far, right? No problem, because I'm going to make it more complex using this. It is like kind of connected all back to here. Any problem? Any question? Is it clear? We have the model, we have the value prediction, the output prediction based on that model, and the label, and we get the residual and sum of the squared residual. Yes?
Just a quick question. Why is it first minus theta hat 0 and then plus theta
Because
1? Shouldn't it be both minus?
no. This is because the model. This is the model. This is y hat. This is the model, linear regression model. This is the label output that we get the difference. So if you look at here, the model that defined is term over here. And this model is defining what? This line. This term, or this term that we used over there, theta 0 added by theta 1, if you replace it with some simple values, you can get this line. This term over here, right side, indicates the slope.
If
Because that x, right? X is increasing. If you put 2 times, what happens? 2 times of x, 0, 1, 2, it will be like line like this, right? If you put 3, the slope is, if you put 1, the slope is goes down. And let me finish. Then after the slope, you can add some value here, theta 0, to increase and decrease where it is. Okay.
Maybe, for example, if you put like for theta 1, the O it's like 2 maybe, and for theta 1 from x it's 6, just like in mine, that would be 6 in total, no, 8 in total, and then we just said which one minus y minus 8 would be y minus 2 minus 6.
Now this is like output of this part over here is the predicted y that gives you some value. Then you say, for example, for this data over here, what is the y? What my model says, the difference. Clear?
Yes, it's not.
Okay. So now we define the residual and we define the RSS, and later here, where we were, okay, yeah, here we define the residual sum of s square, and based on the residual sum of s square that we define, we say now with minimizing the residual sum of s square, we can efficiently find the best line or curve for fit the data. Now whole objective of our model, linear regression prediction model, is to minimize this error over here. Some of the line should be somewhere that this value, the RSS, is minimum. And to do this, we have 2 parts. If you look at the previous equation, we had 2 parts, intercept and slope. And each one had different values. We can put something inside, right? We will see how we can discuss that in next slide. Before continuation, one small reminder to make everything more solid. We had another metric last week. We discussed it. I believe you already know it. Very, very famous mean square error, MSE. So that how we were calculating MSE, to understand better, how we were calculating, it was the average of the sum of the label and the prediction model that we showed last week with f hat of x, that is the same thing. And n was number of the training models that we have. It was looking like this, right? We had the line, and these lines were showing our errors. This equation shows those lines over there. Because this is, for example, at the end data that I have, and the line throws me here. And the differences between these 2 values can give me meaningful understanding. But now the RSS that we defined over here actually is 1 step backward. Why? Because in RSS, we are calculating, I've written the Python code, sum of the y minus y hat to the power of 2, or squared. So the difference is squared. Only sum, but in mean square error, we also get the average. So now we know MSE and we know RSS definition, and both are used for understanding how accurate my model can predict the data that I have that we want to improve it. How this can happen? Let's discuss it. We want to minimize the residual sum of square. The first part that I need to minimize is including intercept error. So intercept has been defined as theta hat 0. And this theta hat 0 can be written like this equation that I want to minimize. I want to find some theta 1 hat and theta 0 in the linear equation that finally leads me to minimize theta hat 0. How can I write that? I can write that the average of the sum of the yi as output subtracted by theta hat 1 times the mean of the x's that I have. So I get the average of the x's. I times them to the theta hat 1, the slope term that I have, whatever I define there, then get the average of the differences between yi and that parameter over there. And yi was the real label value that I have, not prediction. So this equation has been defined for intercept error. I also can show this as y bar, that don't also mix y bar with y hat. Y hat is prediction, y bar is the average. Here we have n as total number of the observation in the data set. Also later we define it as degree of freedom, you will see. We have a note. We can state that measurement of the linear regression accuracy on y-axis can be defined over here with intercept error over y-axis, kind of always considered like bias. It should be up down. So in linear regression model, the model that I'm defining, what algorithm I'm using to do that, I'm intending one step to decrease the intercept error with this term over here. So it looks like this. So let's say slope is something fixed, and intercept is kind of determining which one of these lines are better for my model. If you calculate value with this equation over here, the theta that you have, if you minimize, if you calculate independently for each one of these, you will see that the line over here has lower intercept error. On the other hand, what is the second step? The second step is minimizing the slope error. So what should I do? I should minimize the error for theta hat 1. It means that I want to find some values to put there to minimize the error of model that I have, and it can be calculated like this term over here. Some of the differences between xi and x bar times differences between yi and y bar. The average of the y's and average of the x's times together over the differences of the square of the input. This gives me the slope error. You can, if you are good in math, you can connect it to the correlation and the concepts of the slope in other mathematical problems, then you can understand it better. So I determined that here x bar is the average of the x's simply, and of course like y bar will be the same, and theta hat 1 can be written or can be read as the estimation of the value of the slope coefficient. So far, we understand that we have a prediction line, linear regression. We understand that we have two terms for that. We have the intercept and the slope. We want to find some values to minimize the error that I have over there, to kind of find best value for my model prediction as output. And also we understand that we have the terms RSS and mean square error. Is it clear? Okay. Here, visually, we can show that. Okay, now we want to find the slope. Which one of the slopes of this prediction model can give me better prediction as output for whole data that I have? For example, if you look at this line over here, if you use this line, the error for these 2 points, 2 samples, is very small, but for this one is terrible. And the blue line is the best one that, as I remember, this is the best one that you can achieve with a linear regression. I think I've written code to optimally give you the line of those data. Now, if we summarize these together, we wanted to minimize the slope error, we wanted to minimize the intercept error, and in total, we have the residual sum of B square that has been written in this equation here for the model that I have. So let's have a look. If you want to bring these to code, what does it look like to have better understanding? Let's say we defined a small data set, for example, social media. So these are like some libraries we imported, and a sample data set with advertising data on social media. I just put it 3 values over here. Some values that you are using amount of advertisement on social media. Of course, this data set should be big. Just 3 samples for understanding the concept. We have the X as data, that is social media. X as input, Y as amount of sale that we can have.
Sorry, could you say that again?
No. So this question, you see my watch asking instead of you. Sees that you're not asking. Says, okay, sorry, could you say it again? I want to understand. Smartwatch. Now we want to define here, because we didn't discuss so far how to find those values, theta 1 hat and theta 0 hat. We didn't discuss what algorithm can find the parameters, right? We will discuss it later. I defined the implicit regression model here, that this implicit regression model here exactly determines how we can calculate the slope, intercept, and RSS. I also indicated which line is doing that. For example, I calculated the nominator and denominator, up part, down part separately. If you look at the equation, is exactly what is happening over here, the up part, down part. Then we just need to, for calculating the slope, that we called it as theta hat 1, can be simple division. And for the intercept, we get the mean of the y and subtracted by slope times the mean of the x's, so that it can give me the intercept. And after that, how we can have the prediction, the y predicted. The prediction is the simple linear regression model that I have, right? We said that intercept theta 0 added by theta hat 1 times the x. So this is linear regression model for this one. But this is like implicit definition. We didn't train find the best parameters, whatever it is, whatever comes here. Then finally we calculate the RSS, residual square error, that is the sum of the y, the label data, minus y of the prediction that I predict here, to the power of 2. That exactly determines this equation. Exact implementation of what we discussed so far. How it looks like this. If you run that code, you will finally have this. If you plot it, of course, I will give you later the code. What is looking like, you will have this line over here, the prediction line. And I printed the slope, intercept, and RSS values. The slope is 0. The intercept is some value 20.44, like here. You see that the intercept 24.44. And RSS is like terrible, because the error is too big. This line is not meaningful at all. What we want to do, we want to find these parameters to change the line to somehow like this, to predict better. then its slope will increase, intercept will be showing the intercept, and RSS will indicate the error that I have. So, any question up to there? Clear? Good. If we talk about the goal of the linear regression, we said that, kind of summarizing, we want to find base values of the intercept error and slope error. I determined it as IE and SE here, so intercept error and slope error to plot it. But this SE, don't mix it with another standard error later that is different from this one. Keep this in your mind, that SE later is for standard error. This is just only for plotting the data here. That minimizes the RSS equation, and here another example for the data that we defined at the beginning. And I also plotted different models, model 1, 2, and optimum model that is using the training algorithm to have optimal results, and you can see the parameters and understand what is happening. For example, the intercept error, you can see the slope error over there, and you can see residual sum of square. So if you look at the black line over here is the best fit for the data that I have, right? The others are kind of random, or they train with like 1, 2, or one of the a small portion of the data set that leads us to have wrong data. We will discuss it also. So which one is the minimum in terms of RSS? Is black one over there. The other ones all are getting bigger. Now, let's answer this question, that how to minimize these parameters. There are a couple of different techniques. Today I only introduced them. Later, of course, we will see one of the most common one that we need it more. So one can be done using various, of course, we can use different optimization algorithms in order to achieve it. One technique is normal equations. That is kind of closed form or exact solution for the problem is using the mass. And it is good choice when number of the features is small. If you have big number of data, then it will be computationally expensive, the normal equations. Second technique can be called as matrix inversion. That in matrix inversion, again, we have closed form solution that gives you the exact answer for that problem that you have, for this data set that you have. It is also a good choice when the number of the features is small, again, computationally expensive. And also this has another problem that is that maybe is numerically unstable. In math, we have that problem, numerically unstability. If especially the calculations and somehow define that the small change of input changes the output a lot, so that when you have floating point and you should, for example, 9.33333, you should run it somewhere, for example, you lose some values in some certain degree, so that when you lose some value over there, then it changes the output, and this causes numerically instability in problem that can happen here. Usually is ignorable, but it still is existing. And one of the best algorithms that usually is common in machine learning is gradient descent. That with gradient descent, we can iteratively optimize to use the iteratively kind of change the values of the theta 0 hat and theta 1 hat to finally find the baseline, and it is kind of optimization algorithm that we will discuss it later on and use it in not only linear regression, can be used in the neural network and deep learning models and most of the models that we have. So, of course, we are not also limited to this. There are a couple of other techniques. These are the famous ones. And of course, you know, in Python, we have many libraries that can help us to run, for example, linear regression in 2 lines. You can study which library using which one of the techniques. For example, I think if I'm not wrong, NumPy uses the matrix inversion or normal equations. I've forgotten, but you can study which one is using which one. And if you feed big data set, it's gonna stuck over there because of that. And then there should be some techniques to change it to gradient descent or use some other methods that we will discuss. Okay. Now, let's talk about the standard error. What is the standard error? And if you study especially publications and papers and different research, and output of the models that they propose should be evaluated somehow. And if we have a model, we should somehow evaluate the output. That we have a couple of different ways. The question is, for standard error, we want to answer how precise the estimation of the coefficients are. So what are the coefficients? Intercept and slope. The coefficients we defined as intercept and the slope in linear regression model. So we want to answer the question how precise estimation of the dose are. RSS tells us how well model parameters, for example, regression fits the data. But with standard error of the regression coefficients, intercept and slope, we can say how precise estimation of those coefficients are. It's like one level deeper than the RSS. Not only say how good fit those data are, but also evaluate the intercept and the slope directly. So we can say both RSS and standard error of regression coefficient can be used for assessing performance of the model in decent way, but of course we need them to talk about the model that we have better. Both of them are important, and they are helping us to say the quality and inferring the independence of the variables relationships, and we discuss them to kind of show how the input is affecting the output, how much it is. Let's see. We say the standard error measure of the precision or accuracy of the estimate, and it can be written by this term over here. What we write, we usually show it as a standard error, but we said that standard error should be on intercept and slope. And intercept and slope were parameters of the linear regression. We wanted to find intercept and slope of the model. We want to interpret that one. We want to say standard. What is the standard error for intercept and slope? So what we do, we write standard error of the theta hat 1. That is equal to variance of the epsilon, variance of the error that we have, over the square root of the sum of the differences between inputs, between the input and the mean of the input. So this, if I calculate this term over here, of course I have each one of the xi's that this theta hat 1 determines for me. I get the differences between the mean, I get the average, I get the square root, and the error, variance error over that gives me the standard error. This is the formal definition of the standard error. So we say, okay, usually standard error is estimating using the RSS and degree of freedom in the model. That's how this is happening. So you may say, okay, we said that the variance of the error, we don't have it already. The epsilon, we said that we try to ignore it, but standard error tries to consider that too. How it is considering? We say variance of the epsilon can be written in this form. How? We already know how to calculate the RSS, right? That RSS value after calculation can come here and divide it by n minus 2. What is the n minus 2? N is number of samples in the data set that we call it degree of freedom here. So you have data set. Degree of freedom indicates not number of x's. It indicates how many samples I have in x. This is called degree of freedom here in this definition. Then degree of freedom divided by number of independent variables plus 1. So that here we have the we have 2, because the independent variable that we defined in this example was 1, and we just add it by 1, then put it through here. If we have more, for example, we have 5, we need to write 6 over here, n minus 6. This equation gives me the variance of the error that I have, then I put it here. That comes from the RSS. I could directly write it here. The equation over there, then calculate the standard error for theta hat 1. So what am I doing? I'm evaluating the regression model that I have. I have the theta 1 and theta 0 to determine the intercept and the slope. I'm writing kind of a metric to evaluate how those parameters are over there inside. Why it is important to know? I'm a developer of machine learning algorithm. I'm not claiming, I don't want to claim that I can use machine learning. I know machine learning, but I know how to just import model and train it and get the output. I want to develop new models. If you want to develop new models, if you want to prove that your model is good, you should evaluate it. You should say the parameters that I'm proposing and all the things and how I can do the prediction, the standard error of my prediction values, what is it? If you go study different publications, these are normal, common ways to show the models and the parameters as output. You will see these metrics over paper. So this is for standard error of theta 1. What about the theta hat 0, the second term? We have another definition and term over here, square of the 1 over n added by the mean, square of the mean over the, again, the differences of the x's. That is kind of also looks like variance, because xi subtracted by the mean, that how diverse it is, the square sum, then this gives me the standard error for theta hat 0, the prediction of the theta hat 0. This variance of the epsilon that times here is also the same calculation of the last slide that we've had. We just put it over here, the variance of the epsilon. That comes from RSS. So we say standard error of intercept estimates usually we can say the variability of the intercept term of the population for all possible samples. So you can think now what can be variability mean. Think a little bit about it. If you can guess it, what is it? Kind of says variability of the, for example, you have a data set and your prediction model, how is working in variation of the samples, not only part of sample. How can predict in different variations pretty well over there. It's kind of defining a standard error of that, because also uses the, as you can see, a couple of variances over there inside for example, x's, and takes into consideration of the x parameters. One more note, it provides information of the expected variation of the estimated intercept from sample to sample. And this sample to sample, we will discuss soon how precisely can be. Let me explain next. we say standard error and coefficient intervals calculations. We usually use only entire sample data for doing this. But here we have definition of sampling for standard error. So for standard error and coefficient intervals, what were the coefficient intervals? Let me break it down. For coefficient intervals, we said that we calculate intercept and slope. And for the calculation of that, what we are doing, we are using whole data set. We are using whole values of the x's and y's in order to calculate it. But on the other hand, now we want to define the sampling definition. That, as you know, in machine learning, we usually don't want to train our model based on all data that we have. We want to split it to train set and test set, right? And how we do split to train set and test set, we call it sampling. In statistical learning, machine learning, when we say sampling, you should quickly understand that it's very common. Usually they don't write in the books even, and the definitions, they split it to train, and they say sampling. So when we say sampling, it means that we want to divide. For example, in some cases, 75%, 20% split is appropriate for your data set to for example, train the model that you have based on this data, and then later test it on that 25. Or another understanding can be, you may say, okay, my data set is tremendous, too big. If I want to train based on all those data, it is very hard. I want to reduce it, then you can do sampling. If you have good samples of the whole data in the environment, then you can train the model that works pretty good. So what note we have? The train subset is then used to estimate the regression parameters such as intercept and slope. So now we can say we want to express the uncertainty in estimation by providing the range of the possible values for the true population that we have, true values of the population, that we need to have the constructed based on the standard error, and we reflect the variability of the estimates across all the data set that we have. That this sampling should actually reflect me all the variability of the data set, so that it works very good for the data. For example, when I write code, if I want to show a wrong estimation for you, what I do, like if this is my data set, and this is the line that I can train my prediction, what I do, I say, okay, just use these 2, 3 to estimate. Then if you predict the line, if in proper data, then this will be wrong to demonstrate. If you use these 3, then will be wrong. So that's the whole things that we want to define over here. Okay, I think you look all sleepy now. I don't know why. So I think 5 minutes break, then we continue the topics. Okay. Everybody, hello? Hello, everybody. If you need, wash your face. The class design is somehow I'm teaching here, but those you should look on the other direction. But anyway, I try to sometimes come there too. So let's summarize what we discussed as last topic first. We said that we were talking about, we introduced the confidence intervals first. In confidence intervals, we introduced the intercept and the slope of the model. Then we introduced the standard error. In order to evaluate confidence intervals, we've written the standard error of the intercept, standard error of the slope, right? Then we say that you usually use all data set in order to evaluate this. Whatever we have, we use it. But after that, we say that, okay, we have the sampling topic. That with sampling topic, we say we want to split the data to train and test. And train our model based on the sample data. Whenever we say sampling, we mean that we want to take some part of it. We have different techniques. Later, we will talk about the sampling techniques, right? Now, after that, we introduce the concept of the confidence intervals. With confidence intervals, we want to say how confident we are about the model that we have. And how the parameters are, first we define that. We say we are expressing the uncertainty in an estimation of, in the estimation by estimating the provided range of the possible values. We will define it better in next slides. And we say confidence interval is constructed based on the standard error. So you see they are connected to each other. We first define the model, then intercept and slope. Then we calculated the standard error. Now we want to use that standard error to say what is the confidence interval. Okay? This is also a very important metric in models that we see. And it reflects the variability of the estimation. The confidence interval says how variable my estimate is. So let's see what we do for confidence interval. We use the confidence interval with slope parameter theta hat 1 in linear regression. And we can say that, for example, 95% confidence interval. So this 95% is important. We don't like change it usually. We say 95% of the confidence interval, and we write equation to define it. And we say if we do repeat our sampling and create new train set, then create new regression model, we can say 90% of the times my all data will be predicted pretty fine. What does it mean? It means that, so here, let me, I have this data set. I sample from this data set. It means that I'm not using all. I'm using some of them. And based on that sample, for example, let me indicate some. Based on these green ones, I'm giving a model prediction. Now I want to say, okay, with confidence intervals, I want to make sure that if I redo this, I will end up with the same thing. And I want to say 95% of the time, if I redo this, I will end up with the same thing. Like next time, if I do, for example, sampling of this data, some of them repetitive, again, the model that I have is representing whole data again for 95% of the time. And this is confidence interval. And I need to show to the model that I'm proposing. So you're proposing a model, you're very happy. I have data set, I propose the model, its accuracy is too high. And you publish a journal publication with it. But this is wrong. For the sampling that you've done is working pretty fine. And for the other samples are not working. I've seen this with my eye, with my student, this problem. He has lots of image data set, and he splits the data, samples from data, and brings me an accuracy 99%, 99% point like 5 or something. I get suspicious why this is very accurate, and it was very accurate, really was working. But if this sampling is not working, then your data set, like your data is like this part only, for example, and it works very great here. But for all the model, all the data that you have is not pretty accurate. That's the problem. So already statisticians and machine learning experts develop some metrics for you that you can evaluate how confident you are about your model. So we expect all the slope parameters to fall within this range, 90% of the samples. And how we can write? We should write this range over here. Theta hat 1 subtracted by 2 times the standard error of the theta hat 1 will be left side range, and right side range will be theta hat 1 added by 2 times of the standard error. So that we can write the equation simply. Theta hat 1 added or subtracted together 2 times the standard error of the theta hat 1. And if your values are in range of this minus and positive value, you can say 90% of the time, 95% of the time I have confidence interval that is valid over here. And you need to show for your model this parameter over here. So what we done? We define regression model. We define intercept and slope. Then we define RSS. Then we define standard error based on that. And with standard error, we define the confidence interval. Is there any way to escape to the end? No. We should come from the calculation and we end up here. You can use libraries to make it simpler, calculate inside, but we need to know as developer, and we need to also, like, if you don't understand, like, what is the standard error in detail, then no way. You just see there are some parameters you need to report, you don't understand. You struggle to understand what is it, but you shallow understanding. But now you know, when we are talking about confidence interval, it comes from where? Comes from slope, comes from the error of the slope and intercept, and comes from the range that we want to make sure that confidently 95% of the time my prediction is good. And it doesn't matter, like we are talking about simple problems, linear regression, the most complex deep learning models, you should also do the same. Okay. Now the question is that you guys should answer, what if it does not fall in the range? Why that can happen, and what if it is not in this range? There can be a couple of answers. What do you think? The answer is clear. I drawn one there. What I was explaining here, I said that sampling, then one example is the sampling is not good. For example, the data that we sampled over here shows that then we cannot say 95% confidentially that the next time if we do the sampling from our data and we do the model again, perform the model again, it will be covering all the data that we have. That's one. So let me define different reasons. So it can mean that one or all of these reasons that I'm going to tell you is valid about your model. Why we need to answer it? Because you develop some code, you run some model, and you see some problem over there. You see that is problem over there, and you want to find the reason. You want to find out how to fix it. How to fix it is not like going and reading the code and fix it. Because it's conceptual, you should understand general view and understand generally what's happening. If you don't understand this, if you are a great programmer, you cannot solve the problem. So you need to understand the concept. And concept says that the reasons can be the model may not be good fit for the data, first reason. It is fit, but is not good fit. Completely is not fitting the data. Still you need to improve the model and change the technique that you are using, the parameters or whatever. Sampling approach is not good. We have different techniques for sampling approach. I will introduce some. For example, n-fold technique. So the sampling technique is not good. I mentioned already on these slides. And we can say, okay, this is also very important. There are other factors, other input x's variables that I didn't consider. Because some of problems, like advertising is simple, amount of money you spend, amount of output. But we are machine learning algorithm developers. In some of the applications, we are not too much familiar with even with the data, and the feature is not like 3. Easily, we can 100 different features to consider. For example, in weather prediction, maybe we have 10, 20 parameters. In some applications, we have hundreds of the values, and also they don't have any name. It's not like weather, temperature, or something. There are like 1, 2, 3, 4. And you don't know. You have millions of data for 1, 2, 3, 4, 5, and you don't know what they mean. So how you can, also there are some techniques how to determine those features, and we have automatic feature selection to think that. But you kind of apply some techniques to find it out which one of the features are important. Or in simple problem that is simple, you just take the problem and say, okay, I think that these are important features. But maybe there are some other features that affecting you don't consider. Whatever you do, your model is very good. And your sampling is great approach, no problem. Your algorithm is also great, the best deep learning model. But then says, oh, there are some relationships that you are not considering. Then you cannot predict them. Your prediction never works. Unless you consider this point over here. Clear? Yeah, if the problem is already known, you find lots of examples on the internet, samples that working, you can mimic them. But when you want to really solve a problem that you are a developer, then you need to know the underlying concept and deal with it. Okay, no question? Now let's define hypothesis testing. Hypothesis testing is simple, but also, if you don't listen, complex. So hypothesis testing says that we have a model, we want to express some hypothesis based on that model and data prediction, and we want to later say kind of that hypothesis is true or not in order to prove that our model is good or bad. Again, when you study publications, you see that they say, for example, null hypothesis is done, is accepted. Just write one sentence. Most of you just also you have assignment. You go search on the papers, you see suddenly it says null hypothesis is accepted. That's it. And this means a lot. All the things that we studied so far, that means all the things that we studied so far, and we want to see. Now let's look. We say, and you need to do that and put it in your research and show it, usually. So we say a statistical method, hypothesis testing is a statistical method to evaluate if hypothesis about the approach and parameters is true or not. There are many different hypothesis testings for sampling tests. For example, we have the correlation between two variables is positive. You can say this is like one hypothesis. Is the correlation between two variables positive or not? Or the mean height of the population is 180 centimeters. So you want to say this hypothesis and say if it's true or false. And you can say the proportion of the male in population is 60%, for example. You can state this hypothesis and prove it, and so far. But we have some standard and important hypotheses that already define that we want to make sure exactly about our model. This is the definition of the hypothesis, for example, for data set or different things. The most common hypothesis so far, we have the null hypothesis and alternative hypothesis. So let's see what is the null hypothesis. It's simple. We say we can use standard error that we calculated in order to have hypothesis testing, especially for null hypothesis. And it is not limited for null hypothesis. We can use it for different ones, but that shows relationship between input and output variables, for instance here in regression model. So what is it doing? Using standard error, kind of checks the inputs and outputs relation and says that, okay, this hypothesis can be valid or not valid. So the same definition that I explained to you. Now let's define exactly what is the null hypothesis. In null hypothesis, we have two scenarios, null hypothesis and alternative hypothesis. So null hypothesis can be defined as H0. We write H0, then we say that we have this H0 as null hypothesis that assumes that there is no relationship between X and Y in simplest form. You give the X as input and Y if there is relationship or if there is not. How we show it? We write X0, hypothesis 0, as the theta hat 1 slope equal to 0. So it's clear, you see? It's not that clear, I will tell you. But if first look, you see, okay, the slope is equal to 0. It means that if its slope is equal to 0, then it means that there is no relationship between data, right? There is nothing after training the model. Kind of gives you a simple understanding of what's happening. But we cannot read that value directly. I will tell you in the next slide. You cannot say, okay, this value indicates if it's 0, there is no relationship. So hypothesis 0, null hypothesis, we call it, and show it like that. On the other hand, hypothesis A, that we say it is the alternative hypothesis, and it is in contrast to this. So it is kind of, you can consider if-else's, but they have different names. If null hypothesis, there is no relationship, we can call it H0. Otherwise, we say it is alternative hypothesis, and we say theta hat 1 is not 0. So the proof can be in simplest form. If I explained already, if theta 0, theta hat 1, or its slope is equal to 0, then model from this equation looks like this equation. So we have the y hat equal to intercept added by slope times x, right? This is the linear regression that we defined today. Now, if we replace the theta hat 1 with 0, what happens? This term over here becomes 0. Then we say y equal to theta hat 0. So then there is, where is the x then? then there is x vanish, right? If x vanish, there is no relationship. This is the proof, but this is not enough proof. This is the general, I cannot say enough proof. I mean that this is not enough evidence that we need to also consider something else. Then we say y hat or y, big Y that is showing if we have more than one y, indicates there is no relationship between x and y. Now what we need to do, we need to kind of find a technique to check it, right? Now we define the hypothesis, null hypothesis and alternative. Now we should check it somehow. So the note is that simply checking theta hat 1 is equal to 0 for hypothesis test, as I mentioned, cannot be sufficient to say no relationship between x and y, although it's like clear that shows that we go away with the x. What's the reason? The reason is very nice. The reason is that maybe theta hat 1 or the slope is depending on sample data, and there are many some variability in the estimation value that can causes the other relationship. It's like you have some parameters that you didn't consider, and those parameters causes that you cannot say with the x's and y's that you consider that slope is 0, there is no relationship. If you consider another parameter also, then you will see the relationship. The slope is 0 with that case. But if you have something else too, then maybe the relationship will be visible. Okay. What is the solution then? Or that also another case can be not good sampling. If you don't do good sampling here, you may say, okay, I did sampling and there is no relationship between x and y. For example, if the data was some data was here and the sample was, let me use another color. If I use only this sampling, you see between x and y, predicted y or y, there is no relationship. But actually you did bad sampling. There is a relationship. Because of that, we need to find for some solutions. One solution is using t-statistics. Another solution is using a confidence interval for this specific application. T-statistic calculates the, we need to calculate the t-statistic using estimated coefficient and standard error, intercept, slope as coefficients, and standard error that in next slide we defined. We need to use all of them, actually whole slide from beginning up to here, to calculate the t-statistics in order to say this hypothesis is accepted or rejected. Or another technique is using confidence interval that's similar to what we've done, but this using t-statistics is more common. So now we want to define t-statistics. Why are we defining? We're defining t-statistics to say that null hypothesis is accepted or rejected. Okay, and you will see that we need also add something else. It's not enough still, but anyway, this is machine learning. So t-statistics is a way of the quantifying the strength of the evidence against the null hypothesis. So we want to find some evidence against null hypothesis. That null hypothesis says what? There is no relationship between x and y. We don't want it, right? We want have relationship. and that's called alternative hypothesis. We want to say we want to prove that alternative hypothesis is working, not null. So this statistic is trying to show evidence against it. So we can put T statistics for that one, I explained, and how we can show that. We can show it in this equation. The equation is simple now because we know all the parameters. So T statistics can be shown in the left side, like this form. Usually when you see this, in math we read it in size of, but here it's to determine T statistics in mathematical form. If you see that, you should read it T statistics is equal to theta hat 1 minus 0 over standard error of the theta hat 1. So already we calculated standard error, and we know how to calculate it. Just replace the values of theta hat 1, whatever the value is in the regression model, then get the standard error, then this term will give me the T statistics. Is it simple? Of course it is, if you know how to calculate the standard error. Okay? Now we say, so a larger T statistics indicates stronger evidence against null hypothesis. Whatever this equation gives me, some values are coming out. If it's larger, then stronger evidence. So now we can then tell if accept null hypothesis or if reject. We want to define now if want to accept, if want to reject. If accept null hypothesis, we say there is no enough evidence to suggest that some relationship between x and y are existing. And on the other hand, with a smaller T statistics, we suggest weaker evidence that then we reject the null hypothesis with smaller T statistics so that we go toward alternative hypothesis. And then we say there is relationship. So it's kind of working vice versa, if we accept or if we reject a hypothesis. And there is relationship or there is not relationship with T statistics. But the point is, maybe makes your mind blow, still it's not enough. We say T statistic alone is still not provides complete information about the significance of the coefficient. You should say why we are studying lots of equations, metrics, to say that the hypothesis is working or not. Then finally again we say it's not enough. Yeah, it's not enough because it gives you just some perspective of evaluation. We need to add another perspective too, that called p-value. I think almost impossible. You open a machine learning related or model related paper, publications or book, you don't see p-value inside. And we want to come to the p-value in order to also help the T statistics to evaluate and say that the null hypothesis is accepted or rejected. So the same point. Now we want to define the p-value. For the p-value, let's first define it. So we need to calculate the probability of the observing any value equal to T statistics or larger. Actually, we want to now use the T statistics to make it in form of probability and discuss it. And there are two types of p-values. It's not simply writing one equation over there. And we say one-tailed and two-tailed. And this depends on the type of data that you have, number of inputs that you have. You should choose it. So the p-value is using T statistics, the value plus degree of freedom together in order to give me what I want. And after calculation of the p-value, usually we say, for example, in two-headed one, the different approaches, very simple, I will show you now. We say, for example, p-value of the 0.05 or 5% is often used as a threshold for discussing the statistical significance, or discussing the using that for saying that the hypothesis can be accepted or rejected. So the threshold already given for us, we need to calculate p-value using this degree of freedom and the t statistics. Then based on this threshold, make decisions. So that I also stated that if it's larger or equal to 0.05, null hypothesis is rejected. Otherwise, if it's rejected, we say it is an alternative hypothesis, and vice versa will be vice versa again. And generally, p-value indicates the strength of the evidence that we have against null hypothesis. How it is looking like, the steps I've written here, but a little bit goes too detailed in the math. I want to stop explanation here, but I've written the steps of the calculation of the p-value. For example, you determine the degree of freedom for the t distribution, so that you know how to determine it. But later it goes to look up at the t distribution and how that is. And then I don't want to explain too much more because that becomes a little bit complicated. Then based on that t distribution for one-tail test and for two-tail test, we have different tests and different evaluations, simple evaluations that you can say what's the p-value. And if you want to read more, just refer to this book over here, statistical tools for internet and classroom instructions, that exactly shows in details of this. In statistical learning, they didn't show in the book that we have with our language. They use directly library for this part, and we want to do the same, but this is the details if you want to see exactly how steps are happening. So in Python also we have libraries to calculate, after the calculation of those after having t statistics, how we can perform this on the value of t statistics to get the p-value. And here I've written a simple code for you that indicates what is happening. So for example, the scenario over there, we say if t statistics is smaller than 0, then p-value can be calculated by t CDF of the t statistics and degree of freedom. So I give the degree of freedom that I know, and I give the t statistics as input, then I can calculate the t-value. And this p-value is for one-tailed, and this over here is for a two-tailed. That a little bit different. That what is the two-tailed? One-tailed. The calculation is only the CDF of the t statistics and the degree of freedom. But for two-tailed, we times it to 2, that we want to consider two sides, not one side of the consideration, two sides for the p-value. So we can see Python example. Let me see what I have for you here. Just want to so the example that is in the code, in the slides over here, this part, and first of all I have a sample data, whatever it is, the sample data at the beginning. I hope it's readable for you. Then we calculate the simple linear regression model here. I use linear regression from library for now to show the model. we will learn later how we can train it. We haven't seen to find how to find the intercept and the slope. We said that, for example, gradient descent is about technique. We introduced a couple of techniques, but all of these in background nowadays are, you know, there can be existing in libraries. And for example, from this library over here, I can use it to just give the sample, length of the sample, then it gives me all the parameters that I want as output, but we want to see how we can calculate it down here. Not all of them, some of them, and some other libraries give some other of them. Anyway, down here I calculated the p-value and printed the output plus plotting the data. Let me see what we have here. So very simple data. If you have a look, like very simple, like we have x is increasing, and some data is in the y, a little bit of the like randomness increasing. And we have linear regression model that fits it for predicting the output. And what we printed here, didn't come up very down. The slope, intercept, and t-statistics. After t-statistics, one-tailed p-value, and I've printed that if it's accepted null hypothesis or not. Here I've written that it is accepted, and two-tailed p-value, the value, and if it's accepted, the null hypothesis or not, with some simple if-elses. The point is here that if you look at the implementation, let me see. Here, the t-statistics, I directly put some value, random value inside. I put some random value inside. But what we need to do, based on that data set, calculate it first, then calculate p-value based on that. Why I did that? Because this is your practice. This is your practice to bring everything from the slides to the code and calculate t-statistics so far, then give it to the code. Then you will see how it is working. So I want to also show you this one that I keep continuing. For example, I have shown you one data set, simple random values. Here in this example, for example, social media, TV, billboard, and amount of sale. So these are three inputs, one sale as output. And for example, here I just only use one variable, x as social media, and y as sales over there, okay? Then I calculated the slope and intercept exactly based on the slides. So how we can calculate it. In the slides also you've seen this part of code. Then prediction, then RSS calculation. So I want to run this for you too, so that this is kind of, this code goes to the first part of that you can get the intercept and the slope. Then you can continue with, for example, I've shown like MSE here, mean square error, RSE error, and these will be the parameters that in continuation of the course is coming, and the parameters that we need to learn. Then finally plot them. So let's also run this one. You will have this one too. and this example that you've seen on the slides, and different parameters that printed over there. Then later you need to mix them together and bring it out to finally use the calculations all from the beginning up to end of t statistics and calculate the p-value. Just keep this in your mind that the value here for t statistics, I put something random there that should be calculated. Any question so far? Okay. Now, apart from all of these, we want to have some metrics to see the overall accuracy of the model that we have. Although all of them are kind of slope and intercept, we use it for, also we said that we want to use it to find the best prediction model. And for example, up to t statistics and p-value, we said that we want to use it for hypothesis testing. But now we want to see how we can have overall accuracy of, evaluate overall accuracy of the models that we have. One of them you already have seen, but let's see. First of all, what's the motivation? The motivation is that we need to show models overall accuracy to assess the accuracy, total accuracy, that's clear. Showing differences in different ways of the some, for example, providing more complete picture of how model is working. And each method may have different aspects to show the performance. It means that I cannot say like I have one metric and I can plot it like mean square error, and that's it. It shows that my model is very good. No, that shows only one aspect. We need to use different aspects with different metrics to show the performance of the model that I have, the training model that I have. So how this is working, we say comparing the results from different methods can help also with identifying the potential issues or problems that I have. For example, you measure with metric A, you see no problem. Metric B, metric C shows something wrong. Then you can understand what is wrong based on the metrics evaluation. Maybe two of the metrics are pretty fine, the third one shows something is wrong. Then you can know what's the problem there. It doesn't matter. The problem is simple, or you are training very complex reinforcement learning, deep reinforcement learning, machine learning, deep learning, or whatever you are doing. These metrics will help you to understand what is the model and what's wrong there. So what we have as different metrics, we have a lot, but some of them are very common, very important. Mean square error we already have discussed, very simple equation. We have RSE, residual standard error, second metric. We have R squared, third metric. We have TSS, total sum of square. We have F statistics as another metric, and we have a couple of more. But these are very important ones. We already discussed MSE, but today we want to also see the RSE, R squared, TSS, and F statistics. So, I also want to give you some practices. I think if we start it, you don't have time anymore. So I think I can stop here the course and give you some simple samples that you need to do now in the class to make sure that everything is understandable. Next week we continue with seeing how RSE, R squared, TSS, and F statistic working, because I don't want to also burn your brain. So any question up to here? I was hoping I can finish it, but better to keep it for next week. So let's have a look what we want to see. we want to see the mean square error. We already have seen it. We don't need to see it again. So we in the slides we've seen it. We want to continue with the RSE, residual standard error. We want to see R squared. It's like usually written R to the power of 2, R squared. This is also a very important metric. I think you can see over 95% of the publications. We will see the total sum of square. TSS is not purely usually used. It is used to calculate the other metrics like F statistic. So also F statistic is very important metric that you will see, I think, almost everywhere. So, of course, we have more. These are the most important ones. Later, when we discussing some specific topic, I may introduce one new metric too, depending on the need. But these are the most important ones that we need to know in advance. So again, we are talking about evaluation of model accuracy that we have. Doesn't matter if it's simple model, it is complex model. Here we discuss it based on simple platform regression models. You had assignments, so this week you should do that. After we study this, you need to find a couple of research papers based on your desire, whatever you're researching on, find it and find that they are evaluating these metrics, then discuss it. Say, okay, this paper found that like the statistics in this level, and it means this. R squared is in this level, the values reported for this model are like this, and what is it representing? Already they discussed it already too, if you study it, but I want to make sure that you know what's happening and how you can read them. So let's start with residual standard error, RSE. It is the actually standard deviation of the residual. The name is on it, or residuals can be called as errors. It can be like it is kind of trying to show amount of error that we have, and shows how regression model or the model that we have fits the data. So how the equation looks like, it is like this. We write the residual sum of error is equal to root square of the sum of the differences of the labeled data and prediction, the predicted output of our model. So sum of square of differences of those times 1 over n minus 2. That is n is number of samples in data set that we have, degree of freedom, DOF. We already defined it in previous slides. So this part, first part, if you have a look, we already know it. This sum is already indicating RSS, residual sum of square, that the equation was here. We discussed it at the beginning. So we can then simply write root square of the RSS times 1 over n minus 2. So if we do this calculation, the differences of the labels or the real output that we have with the prediction that we have, again, to emphasize, I'm drawing here. I have a model. So if I consider these are the real labeled value that I have. So for this one, if I want to evaluate this one, this is the y, the value that it gives me, for example, 10, but our model will give me, for example, 7. So I want to find the differences over there, here, simply. So by looking at this, if we calculate the residual sum of S square, we say that the smaller residual sum of S square indicates better fit. It's clear here. If this is smaller, my model has less error, right? This is like the error is low. But here, with linear regression, is very hard. Whatever I do, the error will be. But I want to kind of, so if I want to compare this model with another model, here the error is too big, because look at the errors over here. But this one will be smaller, the green one. So that's why the smaller is better for RSE. So that was second metric in addition to MSE. Now let's talk about the third metric. We are talking about total sum of square, TSS. So we say TSS represents the differences between observed value and Y directly. It is very simple, and we usually, as I mentioned, we use TSS to calculate the other one that we will see. So it actually measures the amount of the variations and equations like this. So TSS is equal to sum of the Y labeled subtracted by the mean of the data that I have, not the prediction. So when you calculate the differences between the Y labeled data and the mean, you get the amount of variation that you have. So here for the metric of the TSS, total sum of square, we say a larger value is greatly desirable. So that we should also consider that this is not only the metric that we can look at it and say our model or our data or our prediction is good or bad. We need to use in conjunction with other metrics. So we move to next metric, R squared, very important metric in order to reporting our model accuracy. It is a metric to evaluate the goodness of the how fit is our regression model, to say this one is good or this one is fitting good, so that it considers the variation. Why is it explained by the variation in X or not? How this is explaining that one? It's kind of R squared try to evaluate it. And how it works, we write R squared is equal to 1 minus RSS, residual sum of squares, over TSS. TSS we calculated in previous slide, and here is the inside of the equation, amount of the variation. If you write the minus calculation of the RSS over TSS, we have R squared metric. So I think it's very simple and clear. You just need to come from the beginning, understand the metrics, and when you understand the metrics by looking at this, you also understand what is happening and what we are trying to represent and show in the model. So usually the output is range between 0 and 1 because it's getting normalized, and the higher value indicates better fit, usually over here. So the R squared indicates how model explains the variance that does not necessarily meet overfit of the model. It means that, okay, so can we, if this shows the variance or variation, so in different models, can we conclude that our model is overfitting or not? It can be a sign, but it's not certain 100% reason that our model is overfitting. So this is a note that you should be considering about. And you already know what's the overfitting of the model. If our model is very accurate to data that can predict in test data set very high accuracy, but in trained data set can work with very high accuracy, but in test data set is not working. And on the other hand, although it is very important metric, although it shows how good our model is fitting, but it is not necessarily can be used solely to again say that our model is good. You should use it with other metrics and usually report it with other metrics. As next metric, we have F statistic that we want to evaluate again model from other perspective. And we say it tests the overall significance of the regression model in hypothesis testing. Now you should load back how was the hypothesis testing. For example, null hypothesis or alternative hypothesis, so that if a statistics is helping us to evaluate it. How this is working, we write f statistic equal to residual sum of square. Again, we are using the previous matrix. Residual sum of square, then over k. That k is number of the independent variables over here. So how many independent variables are indicated? Like temperature, like the humidity, and etc. How many I have here? The k over there is indicating that one. And here again, RSS as was in the top downside, we have ESS over n minus k minus 1. That n is indicating sample size, same as previous that we were considering, n minus k, number of independent variables. ESS divided by that can be resulted in finally representing the F statistic form. So you may think, okay, the understanding the concept of F statistic is not very clear in my mind now. The reason is that you should load back all of these metrics and consider the hypothesis testing, then you will understand what is happening. You should take your time and see exactly what we are doing over here. So with F statistic, we can answer is at least one of the independent variables are useful in predicting output or not. The most important concept that it gives us says, okay, based on this y that I have, at least one of these is important or not. Or I chosen like something, the independent variables that are useless, all of them. Why we should do that? Here you may say, okay, it's clear, temperature will be effective on the weather prediction if I consider. But I'm expert, I can't say that. As machine learning algorithm developers, we should be able to evaluate any data set that we are not expert in. You cannot be expert in any field, right? We can have thousands of problems in different fields that we just have data set. Then you want to write a model that predicts that data set. And based on that, you want to purely understand and evaluate the variables, input and output, and find the relationships. Not only that, so let's say this data is wrong here, or something that whatever we are looking for is not related there. With the metric of the F statistic, we can indicate that yes, for sure there is relationship between at least one of the variables. Today also we will discuss in deep when we are talking about at least, are the others useless? You may think, okay, when I'm saying at least, then we have 10 inputs as x. 9 of them is useless because 1 is useful. No, we will discuss it today in next chapter, exactly. All right. So we say if the calculated F statistic is larger than a critical value or a threshold, we reject the null hypothesis. We can use it as second application over there. With F statistic, we also can reject the null hypothesis. And in addition, we can say a large F statistic indicates the independent variables have stronger effects on dependent variables, and the model is better fit over there. So there are three concepts that I can understand based on first one, that there is relationship. Second one, the threshold, that I can use it for null hypothesis, and over here I can say the how much they are also related to each other. And because of that, F statistic also besides R squared is very important metric that is very common to be used in reporting the model accuracy. We have a Python example. I implemented the code for you over here. That let's have a look quickly. So all these metrics that you see over there are over here. So implementation from mean square error calculation, RSE calculation, R squared calculation. Yeah, is it earthquake? Yeah. Or I feel my chair is moving. Now students are gonna make joke. This professor talks too much, then says don't talk anymore. Okay, I think it's gone. So we have TSS calculation and F statistic. In order of these slides, if you have a look, simply y subtracted by y prediction to the power of 2. The same equation simply has written on the data. So RSE, you can see that calculate the RSE, gets the y and y of the prediction. And first of all, for RSE, we need to calculate the MSE and return it because there we just simply can use the like they were similar. We just don't need to get the mean. So R squared, you see the TSS calculation, RSS calculation, 1 minus RSS over TSS. Simply, we just divided. Exactly same equation that I showed in the slides. Down here, TSS is also, let me remove the mouse. TSS was very simple. Y minus mean of the Y. I get the average of the Y, then Y minus mean of the Y. Very simple, you see. F statistic, a little bit more complex, calculation of the MSE, TSS, find the degree of freedom first, how much the degree of freedom I'm calculating, and the number of the samples that I have. This number of samples can be length of the Y, subtracted by 2, then calculate the 2 parts, and finally calculate MSR over MSE over the variable that I have. Exactly the same equation with some naming over there. So if I run it, let me see. I don't remember what was this. So there is like 2, 3, 4 data and two regression models that predicting them. The objective is to compare them the results. So if you have a look down here, again I think I will not be able to bring this time is good. So if you have a look at here, let me bring back the model also. The objective here to understand what are the differences. So you can see that regression 1 as true, this upper part is true model, that is the blue one, and down one is for this one. So we are comparing different metrics. We want to say, okay, so let's say this is one dimensional, easily I can look and understand which one is better. But in big data and complex data, more dimensions, you cannot have this and look at it and easily say that which one is good. So with metrics, we want to understand which one of the models is better. 2 samples, one wrong, one good one. And if you have a look, mean square error is 4 point something for the true one, but for the wrong one is 7 point something. You see, easily can say, okay, this is better here. Second metric, RSE is 2.08. So for the second one, 2.77. So again, smaller over there. I can compare and say, okay, that's better. TSS for both of them are 40 because it relates on the the mean of the y, the average of the y and the y differences. Both should be same here. And r squared, if we have a look at r squared, here r squared is bigger because we said it should be bigger, 0.4, 0.03 is here. And f statistic, of course, is higher in the true model. So if we go back now here, no, chapter 3. We saw the Python example, and you have your assignment, how to determine the critical value for a statistic, formulate similar to SLAM. So I told you here that we have a critical value or threshold for f statistic, right? For f statistic, I said that we have a threshold that we can reject null hypothesis. So if you remember in previous metrics, I told you what should be the value, but here this is your work to find out if we want to use f statistic to reject null hypothesis, then what should be the value that we look at, if it's greater or smaller, what should make decision. Clear? The answer is very simple, not too hard, just we need to have a look. Now if we want to compare all of them together, so let's bring all. So for mean square error, we said that a smaller mean square error indicates better fit after calculation. For residual standard error, we said that again smaller indicates better fit in our model. For R squared, higher value indicates better fit. For TSS, higher value indicates generally desirable, but usually we don't use this solely. We bring it into the other ones. F statistic, larger indicates that independent variables have a stronger effect of dependent variable. So this is a general perspective of the different metrics that we use for evaluating our models. Is it clear? Any question? Okay, in this chapter we discussed the why relationship between data is important. We saw how linear regression objective can be defined based on the intercept and the slope, and we said that we should minimize those, the error over there. We answered how to check null hypothesis, and we defined 4 different important models for accuracy of the evaluating the accuracy of the regression models or complex models that I have.